Hey, have you ever looked at the back of your phone charger or your TV and seen that little label that says something like 120 volts AC? I mean, we see it all the time, right? But what does that number actually mean? Well, believe it or not, it's hiding a pretty cool secret about the power coming out of your wall socket. And today, we're going to crack that secret wide open.
Visit youtube.com/avidsystem and don't forget to subscribe.
All right, so let's get into it. You probably know about DC, right? Direct current. Think batteries. It's nice and simple, a steady, constant flow of voltage. But the stuff in our homes, that's AC, or alternating current, and we use it for a super important reason. It's way, way better for sending power over huge distances. But there's a catch, a little puzzle that comes with it. The name kind of gives it away, alternating. This voltage is anything but steady. It's constantly on the move.
So that brings us right to the heart of the mystery. If the voltage is always changing, always bouncing up and down, what in the world does 120 volts even mean? I mean, it can't be the voltage right now because in a split second, it's going to be different. So what is it?
Exactly. You're on the right track. See, AC voltage moves in this beautiful, smooth wave pattern called a sine wave. It starts at zero, climbs up to a positive peak, dives back down through zero to a negative peak, and then starts the whole dance all over again. And get this, in North America, this happens 60 times every single second. That's incredibly fast.
Okay, so if it's changing all the time, the logical thing to do is just find the average, right? Makes sense. Let's just average out all those ups and downs. But, and this is a big but, you're about to see why that simple, logical idea completely falls apart and gives us an answer that is, well, totally useless.
So check this out. For that standard 120-volt outlet in your wall, the voltage doesn't just stop at 120. No way! At its highest point, it actually shoots all the way up to about a positive 170 volts.
And since that sine wave is perfectly symmetrical, what goes up must come down and swings all the way to the other side, hitting a negative peak of minus 170 volts. I mean, think about that range. It's bouncing between plus 170 and minus 170 constantly.
And this is where our let's just average it idea hits a wall, a big one, because that positive half of the wave is a perfect mirror image of the negative half. They cancel each other out completely. So mathematically, the average voltage of that beautiful, powerful AC signal is a big fat zero. And that tells us absolutely nothing, right? I mean, we know there's power coming out of that socket. It's not zero.
Okay, so averaging is a bust. We need a new game plan. We've been asking the wrong question. Instead of asking what's the average voltage, we need to ask something much more useful. How much work can this thing actually do? You know, how much real-world power can it deliver to, say, light up a room or charge your phone?
And this right here is the aha moment. Imagine you've got a simple light bulb. You connect it to a 120-volt DC battery, like a really, really big one. The bulb glows, right? Now take that exact same bulb and plug it into a 120-volt AC wall socket. And what happens? It glows with the exact same brightness. This is huge. It tells us that even though the AC voltage is going crazy, it's delivering the same amount of effective power as the steady DC voltage.
So, this idea of effective power, this DC equivalent value, it has a name. It's called RMS voltage. RMS stands for root mean square. We'll get to that in a sec. But the most important takeaway is this. When you see a label that says 120 volts AC, what it's really telling you is that it provides the same heating effect, the same power as 120 volts DC. It's the universal way we compare apples to apples.
Now, I know what you're thinking. Root mean square sounds super technical, maybe a little scary, but trust me, it's not just some random jargon. That name is actually a step-by-step recipe for how we find this magic number. So let's just break it down together. Okay, so funnily enough, you actually do the math in reverse order of the name. First up is square. You take every single point on that up and down wave and you square it. And this is the genius part. When you square a negative number, it becomes positive. So bam, that whole negative dip is flipped up. Now everything's positive. Next, the mean. You just find the average or the mean of this new all-positive wave. Simple enough. And finally, the root. To undo the squaring we did in the first step, you just take the square root of that average. And there you have it, root, mean, square. It's a bit of math magic that gives us that one single incredibly useful number.
And look, this isn't just for a textbook. This is for real. The RMS value is without a doubt the most important number you can get from an AC waveform.
If you grab any multimeter, it's set up to measure RMS by default. Every single power calculation for anything that plugs into the wall relies on this value. It is literally the foundation of how we work with AC power.
Now, as cool as that math is, you don't have to whip out a calculator every time you're curious. Luckily for us, the power from our walls is a really clean sine wave, so there's a super simple shortcut. All you have to do is take that peak voltage and multiply it by about 0.707. That's it. It'll give you the RMS value every time. Super handy.
All right, we've got all the puzzle pieces on the table now. Let's put them together and finally solve the big mystery we started with. What is the hidden secret behind that 120 volts we see everywhere?
And here it is. That 120 volts you see printed on everything, that is the RMS value. It's the effective value. It's the number that tells engineers and your devices exactly how much work that wall socket can actually do. It's the number that matters.
But here's the mind-bending part. In order to deliver that effective power of 120 volts, the actual voltage is peaking way, way higher. It's hitting about 170 volts, then dropping to negative 170, 60 times a second. So the number on the label isn't the peak, it's the power it's equivalent to. That's the secret. So let's wrap this all up. What's the main takeaway? Simple. That 120 V from your wall is the RMS value, the effective value. It means it does the same job as a 120 V battery. But the killer fact to remember is that to do that job, the voltage is actually peaking at a much higher 170 volts. And this whole clever RMS system is the reason we can reliably design every single electronic device we plug in. And that leaves me with one final question for you. Now that you know the peak voltage zapping your electronics is almost 30% higher than what's on the sticker, how does that change everything for the engineers who design these devices? They have to build every single component to survive that higher peak, not just the RMS value. It's a pretty big deal, isn't it? Something to think about next time you plug something in. Thanks for joining me on this one.
Thanks for watching.